mean, I'm sure you all know this. You've already seen Rn. It's probably like the only vector space anyone gets anyway. Well, you're supposed to get other ones eventually, but whatever. And so, and I'm sure you guys know you can define an inner product on Rk. We also define x dot y to be equal to x1, y1 plus only x2, yk. And this is an inner product. This is an inner product on wonderful. But we knew this. This is the dot product. This is just adding vectors and multiplying by a scalar. No questions about that, I hope? I mean, if there are, that's fine. But you guys have all seen this? Right? This was like Math 54 or linear algebra, whatever it was called at your school. Oh yeah, and I forgot to tell you, and we defined the norm of a vector to just be x dot x to the 1/2. Or another way of writing that is just the sum from, oh gosh, gotta be careful, j equals 1 to k, xj out squared to the 1/2. Yeah?
You also assume the Euclidean space is not empty.
It's certainly not empty, right? Because I mean, it's finitely many things. I can name an element in there. For instance, 0, 0, 0, 0, 0. That's it. My point is, you can, since this is just a finite copy of things, you can name an element in there, no problem. You don't even need something like the axiom of choice to show it's not empty. Which you guys don't actually know what it is yet. Yeah, there's this. I mean, maybe you've heard of it, but there's this axiom called the axiom of choice, which is like the most nightmarish thing in the world because it does everything from like create paradox, like one of my favorite paradoxes is called the Banach-Tarski paradox. It says there's a way to take a sphere, go in there with like a perfectly fine razor, cut it up into 4 pieces, take the 4 pieces apart, put 2 of them together, put the other 2 together, now have 2 spheres of the exact same volume as the previous one. This is called the Banach-Tarski paradox. It's a consequence of the axiom of choice, which I don't think I'm going to talk about too much in this class, but like, it's basically the axiom that everyone's just kind of like, we just we sweep all the problems under the rug and we pretend there's not too many issues. Because it creates all these really weird paradoxes, but it's still like, all it says is that like if I have a lot of sets, like I have some number of sets, some large number, doesn't matter. I can take one element from every set. That's all the axiom of choice says. That if I have, no matter how large a collection of sets, so it could be, make sense of this next week or tomorrow, an uncountable number of sets, I can take one element from every set. That seems reasonable, right? Because if I have 7 sets, I can certainly do it. Hell, if I had a line of sets, I could certainly do it. But it turns out if you assume you can always do it, you create all these paradoxes. It's really weird. Anyways, proposition. Just some simple properties. I'm not even going to prove these. I just want you guys to know them. The norm of x is always greater than or equal to 0. I think this is fairly obvious, and it's only 0 if and only if x is 0. And by x is 0, I mean it's the all 0 vector. 2, the norm of some scalar times x is just equal to the absolute value of scalar times x, which I haven't actually defined, but I'm assuming you guys know what that means. I mean, right, the absolute value is, if it's a positive real, it's its number. If it's a negative real, it's the opposite, right? You guys know what the absolute value is. I was going to define it, but then I'm like, why waste your time? Sorry, the absolute value of x dot y. So I'm not going to prove this one just yet, I'll prove it later. This is called the Cauchy-Schwarz inequality. According to Rudin, it's just a Schwarz inequality. Maybe he was good friends with Schwarz. I'm just trying to cut Cauchy out of it. But this class wouldn't exist if it weren't for Cauchy. His name is going to haunt you. We're going to talk about Cauchy sequences and Cauchy this and Cauchy that. Cauchy was the guy who like said, like, a bunch of people were complaining that like Newton's calculus was like didn't make any sense because you add this you add this epsilon or divide by this epsilon, saying, oh, it's not 0, we can divide by it. Then you let it be 0. That's how you take like derivatives. So people, in fact, this institution's named after the guy who did this, I think. But the Bishop of Berkeley, or Barclay, was one of the major people who said calculus doesn't make any sense. You're like dividing by things and then making them 0 later, right? And he was complaining about this. So a guy named Cauchy, who's also like one of the most insane mathematicians I've ever heard of, decided, okay, I'm going to make everything rigorous, and he basically came up with this class. I mean, other people helped, but Cauchy was like definitely the spearhead of the project that made calculus rigorous. Right, you guys probably know the triangle inequality. I can prove that for you if you really want. And then what's the last one? I think I had another one. Yeah, I did. And then this thing, this is kind of stupid, but this is the norm of x minus, this is just a restatement of the triangle inequality that I think I'm going to use in a proof later anyway. X minus y. So this is, I should tell you where everybody's coming from. X, y, z are k. X minus y plus y minus z. All right, cool. And I mean, you guys, so I'll ask you, I'll let you guys decide. You guys need me to prove these things? I'm Rudin as the person in the book, but very straightforward, I think. In fact, Rudin's proof for one, the first two is it's obvious. And Rudin's proof for, well, this guy I'm going to prove it in a minute, but I'm going to use the complex numbers to do it more generally. And this guy here is pretty easy. See if yeah. This guy's really easy. You just square both sides and you show that it's obvious. But I can do it if you really want me to. Are we happy with this? All right, cool. Just great. So I just need to put them up there so no one says you never told me this. This is like my lawyer said I had to do this. All right? How are we doing with time? Great. Let's take a break. 10 minutes from now, so that's at 16. We'll come in. We'll do the complex numbers. Tomorrow's going to be tomorrow I did think is going to be mostly a work day. We're going to start with the worksheet. Then for sure, even if we don't get to it today, tomorrow we're going to spend at least like 30, 40 minutes on the worksheet. I want you guys to work with each other, come up with some ideas. We'll talk about a few of the problems. Then we'll jump into chapter 2. So, great.